Flapping wing aerial vehicles have advantages in good flight maneuverability and efficiency. We can observe in nature two main flapping modes, horizontal plane and vertical plane flapping, followed by a quick slicing upstroke. The implementation challenges lie in unstable body orientation. Therefore, active modulation with feedback control systems or added dampers are essential. However, as aerial robotics converge to tiny scales, implementing these systems limits size and maneuverability. Jellyfish-like ornithopters were able to overcome stability issues with a bottom-heavy design. Opposite pairs of wings oscillate to produce an upward force and is tethered to external power supply. In the future, it may be possible to add a battery and also active stability for increased directional control. Robo-bees have independent piezoelectric actuators for individual wing actuation. Like bees, these conserve energy by perching to surfaces using electrostatic adhesion with an electrode patch supplied with charge, and to detach, the charge is switched off. The fabrication process involves a non-intrusive pop-up method. However, the tethered wire limits the potential for aggressive maneuvers. The Batbot's thin, stretchable silicon-based wing membrane amplifies the actuators, morphing with the airflow, which increases the thrust force when air is pushed back. The Batbot targets the complex movement seen in bats and simplifies 40 joints to 5 active joints that move independently. It is launched by hand and lands in deep store. At low Reynolds numbers, fluid is prone to more separation, leading to high drag and lower efficiency. Also, the low aspect ratio wings mean that the wingtip vortices affect the majority of the wing, reducing the effective angle of attack. Due to small-scale desirability, it is challenging to integrate independent flight with microscale sensors and power supplies for sufficiently long flights. The low inertia also makes them very sensitive to the wind. Strict laws regarding the study of live animals challenge further potential biomechanic research. Flapping wings could be applied to surveillance, household cleaning, environmental sensing and pollination, with additional implementation in swarms and group communication. The future directions of flapping wing aerial robots possibly lie in drag reduction, underwater applications and continued research on biomechanics, as well as integration with other thrust sources.